And I should comment that I've never seen a lunar occultation, but there was one during this experiment. Here's the knife edge diffraction as the Cassini beam is occulted by the moon. And on this night we had rain, hail, a lunar occultation, and a solar mass ejection, a coronal mass ejection. So the data were not going to be very good that day anyway. Let me just summarize what the data are telling us. I think that the Ka band did knock the plasma out of the equation as it should have. The two-way Ka band data, which are selected for high elevation angle but not corrected, are at the level consistent with what we expected before the experiment. There's a problem in that it rained some of the time, and so some of the advanced media calibration data are flagged, and liquid water in the beam, well, actually the advanced media calibration system doesn't work well when there's liquid water in the beam, so some fraction of the data will have degraded sensitivity. Well, anyway, yeah, that worked. We saw some problems on the ground with antenna mechanical and systematics, but we think we understand those. But what are the prospects for ultimate sensitivity? Well, the three canonical kinds of waveforms are bursts, backgrounds.
So what is going to be your level of sensitivity from the scene?
I'm about to show you. I'm about to show you what I think it will be. For bursts, it depends on where you are in the sky. And if, for example, you have a hypothetical damped sine wave, you can, if you play that through the 3-pulse response and then do match filtering for what that waveform looks like, you get a different output of that match filter depending upon where in the sky it's coming from. Because the effect on the gravity of the gravity wave is to shake the spacecraft, if the gravity wave is going, if this is the Earth and this is the spacecraft, so the beam is back, if the gravity wave is coming right down this this direction, it's shaking the spacecraft and the Earth this way, and so there's no effect to first order in the Doppler. So you have no sensitivity along the Earth spacecraft line. Here's where the spacecraft is in December 16th. This is a right ascension declination equal area plot. So you have no effect here and no effect in the opposite direction. The contours here are contours of constant match filter output. So basically red means, or orange means good, and blue means not so good. Unfortunately, Andromeda is in a not so good position, and the galactic center is in a not so good position, and the Magellanic clouds are in a not so good position. So at least with respect to members of the local group, the first experiment is really not very well oriented in space. If you wait until 2004 and look for the same waveform, yeah, same waveform, then things get a little bit better. The galactic center has crept up into the point where its match filter output is pretty good. And I'll show you numbers in a second. This is the plot that may make the most sense.
People understand why you have these discrete tracking periods when you get good data.
I should have mentioned that we really want to do this experiment in the anti-solar direction when the plasma in particular is at a minimum. The Ka band knocks the plasma out, so we have more flexibility than we used to. But still, experiments done at the VLA and other places show that the troposphere is the most stable in the middle of the night. So there's reasons for preferring it in the middle of the night anyway. You don't want to do it across for the troposphere's point of view, across a sunrise-sunset boundary, because you have convection and it's just not as good. This is the plot that may make the most sense to you because it's the analogous plot to the Lisa sensitivity curve. If we were to have this assumes that we have 40 full days of tracking at Ka band, which is not quite right because we get one third of a day each day for 40 days. So I'm imagining then that we could stack up the three experiments this way. So what's plotted here is 1 sigma sensitivity based on averaging over the sky and over polarization states for gravity waves as a function of Fourier frequency. Here we have degraded sensitivity because the SNR limit, the finite SNR in the downlink, We have oscillations in here which relate to the various transfer functions of the noises, and Massimo Tinto is an author on a paper which elucidates this in physical, I don't remember the reference, but I'll get it. Yeah, right. And we get degraded sensitivity at low frequencies for two reasons. One is our noises become red at some point, and more importantly, we get pulse cancellation, so we're losing sensitivity for that reason down there. So you're used to seeing, for LISA, numbers that are about 10 to the minus 23, and it's more like 10 to the minus 16 here. So
pulse cancellation is when the two pulses overlap and then cancel out.
To first order, yeah, right. So down here, it's not like you get no sensitivity. It's just that it goes away.
Also, the lasers are getting.
That's right. Yeah, the noise gets worse down there too. So it's a combination of those two effects.
So you said your goal was 10 to the minus 15, but you're achieving 10 to the minus 16.
Let me move to the summary then. It depends on what waveform you're talking about. So I'm going to do these in an inverse. The last three view graphs I'll do in reverse order. This was meant to be the punchline. So this is the punchline is that I think we're aiming for 3 times 10 to the minus 15 for bursts.
This is a significant signal to noise.
This is signal to noise ratio. Well, this is Allen deviation. So that's SNR equals 1. Now, for a given waveform, you can beat this depending upon the shape of the power spectrum and the shape of the signal. But in a non-committal way, this is roughly speaking what I think we're going to hit. And we won't hit that all the time because when it was raining, about 25% of the time, we won't be able to do the calibration. I think we'll get down to about 10 to the minus 2 of closure for backgrounds. And I don't think we're going to quite do as well as I showed you in the previous graph. That previous graph averaged about 1.5 times 10 to the minus 16 over the band for periodic waves. But we'll do a little worse than that, I think, because we won't get the full effect of the Ka band without taking all three data sets together, and even then it's raining some of the time. So loosely speaking, a few times 10 to the minus 15 for burst, 10 to the minus 2 for closure for backgrounds, and depending upon where you are in the band, I mean, if you're totally optimistic, you might say several times 10 to the minus 17, but I think that would only be at selected frequencies even if everything else worked well. So let me just remind you that Doppler tracking is in principle, it's a broadband detector. Apparatus large compared to the wavelength. Not an interferometer, so coherence has to be maintained through frequency standards. And the main noise sources I've dwelt upon because the noise is actually in many ways a substanceless experiment. So let me just conclude with this last slide, which is would it make sense, to what extent does it make sense to push this technique any harder? These are the main problems. Plasma scintillation is really not a problem because we can beat that just by going to higher radio frequency. Tropospheric scintillation, antenna mechanical noise, FTS noise, and spacecraft position noise are all non-dispersive, and so you have to deal with those directly. There's no tricky way to do it. There are approaches for each of these things. There's a neat idea that Frank Estabrook and Ron Hellings came up with. An even better idea might be to put it on top of the antenna on top of a really high mountain, so you're above the troposphere. Antenna mechanical noise, you're limited there by the strength of materials. You're not going to change how antennas are built, and if you need them to be big enough to collect the apparatus, you're going to have antenna mechanical noise. And so probably that means that if you want to do significantly better, you only be able to look at those frequencies which are the nulls of the transfer function for antenna mechanical noise. Spacecraft position noise you might be able to improve upon by very careful design. Right now it's 2 times 10 to the minus 16. Maybe you could do better. Frequency, I'm told by the experts that if you only gave them money, they would give you a 30 times better clock, so that's not a problem, except insofar as you've got the money. So maybe the conclusion is that you might be able to get at selected frequencies down to several times 10 to the minus 18 with this technique, if you were willing to spend a lot of engineering effort. But the cost would be very high, and you'd have to ask the question whether the money would be better spent pushing this technique to its limit, or to invest that money in a new technique like LISA instead. And so I've overrun by 5 minutes, so maybe I'll in one or two questions if there are any, and then I'll get out of the way. Great, okay. Very good.
Okay, in the remaining time, I'd like to talk about another technique for searching for gravitational waves, which, like the Doppler tracking of spacecraft, is a technique that has been under development and in use for a number of years. This is the technique of pulsar timing. Pulsar timing is a technique that is used in the VLF band, very low frequency band, which is the band where the periods of the gravitational waves are of order 10 to the 8 to 10 to the 9 seconds typically. That is a few years. That period is set by a graduate student lifetime. The technique you've just heard about of Doppler tracking of spacecraft, well, a graduate student lifetime and professor lifetime, they're in the same order of magnitude. Okay. Doppler tracking of spacecraft operates like LISA in the low frequency band, which is set by basically the scale of the solar system or the inner parts of the solar system. So it in fact has good sensitivities and periods ranging from 10 seconds out to something like 10 to the 4 seconds or a few 10 to the 4 seconds. Let me just remind you that the energy density in gravitational waves goes as the wave amplitude times the frequency quantity squared. That is, it goes like the first time derivative of h quantity squared. And so in order to have the same energy density in different frequency bands, as you go to lower and lower frequencies, you can have larger and larger h's. And so this is associated with the fact that when you look at sources, you find the predictions are, as you go to lower frequencies, your sources tend to have larger h's as well. Fortunately, that partially compensates for the fact that as you go to lower frequencies, the technology gets harder, tends to get harder. And so, as you will see, pulsar timing is capable of reaching today h's of order 10 to the minus 13, compared to the Doppler tracking, which is sitting at h's of order 10 to the minus 15 until you do something fancy like search for something that has a large number of cycles where you have a template where you can go down below that. The characteristic figures of merit are 10 to the minus 13, 10 to the minus 15. And I remind you that in the high frequency band of Earth-based detectors, the characteristic numbers that are currently achieved are of order 10 to the minus 19, and LIGO by next year or so ought to be in the vicinity of 10 to the minus 21. Okay. But you are at much higher frequencies, and so for the same energy density, you have to do better at the higher frequencies in order to have any success. Okay. So let me describe the technique of searching for gravitational waves by pulsar timing. The basic idea is that you have a pulsar, which is a spinning neutron star spinning around some axis. It has a electromagnetic beam that shines not off of its surface, but out of its magnetosphere in some manner. And as the neutron star spins, that beam swings around and around in the sky. And so in the direction toward the Earth, where you have a radio telescope just of the same sort. In fact, the telescopes that are used at the Deep Space Net are sometimes used or have been used for this purpose, the very same telescopes. You sit out here on Earth and you look for the waves coming from the pulsar, the electromagnetic waves, and you see the radio waves coming in, and they're in the form of sharp pulses every time, well, sometimes not so sharp, every time the star spins one revolution, you get a pulse. Or in some cases, you may get 2 revolutions per pulse because there may be 2 beams, one coming off the other side. And so the basic idea in Doppler tracking is that you have then a gravitational wave that is coming in from some direction. Here are the phase fronts of the gravitational wave. It travels toward Earth, and as it travels toward Earth, it ultimately reaches the Earth. It buffets the Earth in the same way as it does in the technique that John just talked about. And similarly, if the source of the waves is extragalactic, as is the case for all plausible sources in the VLF band, but this pulsar is in our own galaxy, which is the case. These are the pulsars that are strong enough for us to use to apply this technique to. Then the wave will come in, it will interact first with the pulsar, moving it back and forth, and then it will interact with the Earth, moving it back and forth. And so if you are measuring the same thing as one does in the Doppler tracking technique, if you were measuring a change of frequency of the waves, delta nu over nu, you would see from a gravitational wave, say that is in the form that just has one sharp burst, it goes up and down and stops. You would see a blip associated with the interaction with the pulsar and a second blip associated with the interaction with the Earth. And so instead of a 3-pulse signal, you would see a 2-pulse signal. Yeah.
But the difference between the two, the time difference between the 2 blips would be of many years.
That is the case unless the wave is traveling nearly parallel to the propagation direction, in which case it could be shorter. And in fact, the waves that we're going to be talking about, then the only plausible, well, the most plausible waves are well, let me back up. As we will see, in order to get adequate sensitivity, you have to deal with waves where you will only see one or a few periods of the waves in a graduate student or professorial lifetime. And so we, in any case, we will not see the same blip from here and from there unless you are absolutely aligned, in which case the strength of the signal goes down. But on the other hand, perhaps the most plausible sources are supermassive black hole binaries, which are not in the process of merger, but are in the process of inspiral. And in that case, you may actually see both the waves from you may actually see the waves from here and from there, just because the signal is going on and on and on and on. Okay. So that's the basic idea, and except that instead of making measurements of the fractional change of frequency, which is the best way to analyze your data in the case of Doppler tracking, the best way in this case, because you have these very steady bursts of radio waves that are carrying your signal, the best thing to look for is a change in the arrival time of this signal back here relative to where you would have expected it to arrive based on all the preceding signals. So the best thing to look for is some fluctuation in arrival time of the pulsar bursts. And so what one then looks at is the time of receipt of one of these bursts. Actually, you take a large number of bursts over a period of, say, a day, and you average over them to get some average time of arrival for things that day. So a burst arrival time is what you measure, and that should be the same as the emission time of that burst, plus the time that it took for the burst to travel from the pulsar to the Earth, the distance L, so L divided by the speed of light, assuming that there's no dispersion. And what is actually done is to correct for dispersion. You make measurements at several wavelengths and you correct for dispersion in order to determine when it would have arrived if there were no dispersion. Then there will be some residual. And it's that residual that one actually measures. And it's that residual that one wants. Of course, in order to determine the residual, you really need to be able to predict when that pulse should have arrived, which means you have to have extensive studies of this particular pulsar in order to know just what it is doing, what its interpulse period is, how that period is changing because of spin down of the pulsar, perhaps even second time derivatives of that period. And if the pulsar happens, as some of these are, to be in a binary, you need to learn everything you can about the binary. If the pulsar happens to have planets, as is the case in some of the pulsars that people use, you need to learn all about the planets and the motions on the pulsar that are created by the planets. You need to remove those from the data. The final thing after you've removed all the systematics about everything you know about the pulsar from the data is the residual, and that's where the gravity wave signal lives, together with lots of noise. Now, in the exercises that I'm going to give to you for this week, there's a nice exercise to derive this residual. And what I will do is I will have you derive this residual, the influence of the gravitational wave on this residual, for this problem of the pulsar timing. I will then have you differentiate it with respect to time and let the signal come back, and you're dealing with Doppler tracking, and you'll get the answer for Doppler tracking. And then I will have you let the wavelength of the waves get longer and longer until they overlap, and you can get the signal for LIGO. So you basically, and I'll have you do the signal for LISA as well. So in one exercise, beginning with the problem of the pulsar timing, you'll work out what the signals look like for all the various techniques of gravity wave detection that are currently in use. Okay. So what is the answer for the residual? The residual, in fact, turns out to be given by a very simple formula. What you do is you integrate along the path that the photon travels. So the integral is along the pulse ray. So the pulse is traveling on a ray in the sense of geometric optics through space-time. You integrate along the pulse ray the gravitational wave field, say H+, and integrate it with respect to distance traveled. Let's say dr over the speed of light, where r is distance traveled, times a coefficient out in front, which depends on the polarization, depends on this angle theta, which I'll let you work out the details of. It's a coefficient that is of order unity. And so it's very simple. You just integrate up h, is the h from the waves, whether they're plane waves coming in or some other kind of random waves that are somehow focused. It doesn't matter what they are. You just integrate h along the ray from the source to the Earth, and you get the answer. In the case where these waves are sinusoidal at an angular frequency omega, then most of the integral just cancels out because you're integrating a sinusoid. The piece that doesn't cancel out is any residual of a fraction of a wavelength here at the Earth, and any corresponding residual of a fraction of a wavelength there at the pulsar. In order of magnitude, what that's going to give you is something that looks like h divided by omega, or it looks like h times 2 pi times the period of the gravitational waves. Now, considering periods that might be of order, say, 10 years, so this residual looks like h. Let me put in 10 to the minus 13, which is, I claim, is basically the state of the art here. And then we have a 2 pi, and then we have a period, and the period is, say, 3 times 10 to the 8 seconds. And I've got my 2 pi in the wrong place. Omega is 2 pi over the period. I wish it were up here, but unfortunately it's down there. And 1 over 2 pi is approximately 1/10. So we get 10 to the minus 13, 10 to the minus 14, and a 3, 10 to the 8. So that's about 3 microseconds. So an h of 10 to the minus 13 gives you a residual of order a few microseconds. And the current state of the art in this business, the current state of the technology, is to be able to predict the pulse arrival times to a precision of order a microsecond. It's clocks that are stable to stabilities of order a microsecond, the clocks here on Earth. It's other noise sources that you deal with that are at basically that level. So let's compare that let me first give you a similar thing in terms of the amount of energy in the gravitational waves. So let me remind you then that we generally talk about the energy in the gravitational waves in terms of the critical energy to close the universe times some fraction of that is in the gravitational waves. So if the energy in the gravitational waves in a bandwidth equal to frequency were equal to the critical frequency, then omega would be equal to unity. And as John said, the state of the art with Cassini is going to get to an omega of 10 to the minus 2 in the Doppler tracking of spacecraft business in the low frequency band. And we can see what this 10 to the minus 13 corresponds to in the very low frequency band. And so the issue is that this energy density, ignoring factors of 2 pi for the moment, it just looks like h times f quantity squared, where h is now the root mean square fluctuations of the gravitational field in some stochastic background in a bandwidth equal to frequency. Okay? And so that's the energy density. And so that means that h RMS is of order rho crit omega gravitational wave divided by frequency squared, and then I want to take the square root of that. Okay. So what did I do wrong? That's right. And then the residual that is the observable that the pulsar timing people work in terms of. That residual looks like the HRMS divided by 2 pi times frequency. That is divided by angular frequency. Okay. And so that looks like rho crit omega gravitational wave over f to the 4th inside the square root. That is, there's an f squared here. I pull this f inside the square root, and I've got an f to the 4th. And it's this f to the 4th that the pulsar folks are really working on. The idea is that if you can live longer and longer, then you can go to lower and lower frequencies, and you can get to an omega that improves as the 4th root of how long you live, or how long you collect data. Of course, the other thing that you can do is try to improve your residuals, do the experiment better. And so you have those two techniques. But you win enormously in terms of frequency if omega is more or less independent of frequency. And so that is the name of the game. Now, let me just give you a number here. So this, when you put in the factors of 2 pi, this goes to something like an omega gravitational wave over 10 to the minus 8 times frequency in the units of 0.1 cycles per year to the 4th power, and then the square root microseconds. So with residuals of order a microsecond and working at gravity wave frequencies of 1/10 of an oscillation per year, that is a period of 10 years, one can get down to an omega of about 10 to the minus 8. Okay. So the best measurements to date is our data, collecting all the data together at their disposal that Don Backer's group at Berkeley has done. And this is from a PhD thesis of his student, I believe it's Adrian Lohman. But it's not yet published. They are working at a period of 17 years because they have data that span a length of time over some 30 years and rather good data over some 20 years. So working in a period of 17 years, they can do better than this 10 to the minus 8 by a factor of 1.7 to the fourth. So they have an omega GW that's of order 10 to the minus 8 over 1.7 to the fourth. Well, that's approaching 10 to the minus 9 or 2 times 10 to the minus 9, something like that. So that's basically where they are at with microsecond residuals. And so the question then is, where do you need to be So I will give you a paper to read by Roger Gopal and Romani, in which they, by population synthesis, estimate the strengths of the gravitational waves that are produced by the superposition of the emission from all the supermassive black hole binaries in the universe out in this frequency band. And it's the very massive ones that are dominating now, the black hole binaries with masses of 10 to the 9 of a few times 10 to the 9 solar masses. So these are the really massive ones. And their estimate is that omega GW is of order 10 to the minus 11, roughly independent of frequency. Not precisely, as you will see, but roughly independent of frequency at frequencies of order one cycle per 10 years. So in order to get to this source, what is needed is an improvement of about 2 orders of magnitude in omega. That corresponds, since the residuals go as the square root of omega, it corresponds to improving the residuals by about a factor of 10. So you would really like to get down to 1/10 of a microsecond in the residuals. Or living a factor of 3 longer. That is, in a worst case, if you can't improve the technology, you go for periods of 60 years instead of periods of 20 years. Now, the technology is going to improve. When you're dealing with increases from 1 year to 5 years to 15 years, you are really winning. But it's a lot harder to get from 17 years to 60 years, which is your next big factor. And so the big struggle is going to be in improving these residuals, and the hope is that on the same time scale as LISA, probably not on the same time scale as advanced LIGO, that these residuals can be gotten down by another factor of 10, and one can, at least if the predictions are correct, one can see these waves from stochastic background of massive black hole binaries, and quite possibly see the waves from the very brightest binary in this population. However, there's one cautionary note about what we're going to get out of this, and that is that if you are being forced by the strengths of the waves to operate at periods where the period is of order your observation time, you're not going to get a lot of information out of the waves. I mean, you'll get a few bits of information, and that's all. And that's the advantage of operating at higher frequencies. At higher frequencies, you've got a lot more bandwidth in which to collect information, a lot more periods in a graduate student lifetime, and so a lot more information available. But it's different kinds of information. There's no way with gravity waves to observe black hole binaries of 10 to the 9 solar masses with any other technique. This is the only technique that because those waves are emitted in this band and they're not emitted in the LISA band or the LIGO band. And so this is of considerable interest, and it is getting close to where one would like to be, but it's not there yet. And that improvement of a factor of 10 in the residuals is going to be quite non-trivial. It's going to involve building up an array of pulsars and doing timing on an array of very quiet pulsars. And the pulsar astronomers are in the process of building up such a very quiet array. It's going to involve improvements in the clocks that you deal with, and improvements in various other pieces of the technology that go into these experiments. Gee, I get a hand too? Thank you. John?
If you were just if the gravity wave was shaking the Earth, then shouldn't it be true if you're timing a lot of different pulsars, and in addition to you take a lot of time, shouldn't you expect to see a quadrupole or some kind of very fluctuation?
So you will see a pattern, but the pattern turns out to be more complicated than just a quadrupolar. Because of the issue of the way that the waves influence the pulsar. So it will really depend. If this is if these are, so the waves influence the pulsar as well as the Earth. And so if you do a cross correlation, a better way to say it is if you do a cross correlation between what you see on a number of pulsars, then you will get a pattern that is more or less quadrupolar. But if you don't do a cross correlation, and you just, in order to remove the uncorrelated noise between different pulsars, if you don't do that cross correlation, you won't see it. But with cross correlation, I think you should see it. But as far as I know, the details of how to do the data analysis, how to do that cross correlation, just what you really get, I don't think that's ever been studied to my knowledge.
And Ron Hellings and also by Romani and Taylor some time ago. I'm not sure that, I don't remember what they did.
No, they may have. I don't know the literature very well. Yeah, I'd like to know. I don't know the literature well. Okay.